Hello, everybody. How are you?
Good.
Oh, wow. Well, this is
Wonderful.
great. So hello, that was Megan, by the way. We're really happy to have these amazing co-hosts with us today. I always want to double check to make sure our sound is working all the way through to our Ask Math Anything. And at this part, this is the part I usually explain what this is all about. James Lettuce. I love these names. I love it when we say intentionally, please give a fake name, because then we can see how creative everyone can be. So you can hear me. That's great. Okay, so let me just tell you how this goes. This is called an AMA, which stands for Ask Math Anything. And who's representing math? Well, actually not me tonight, but two incredible people. Those two people will introduce themselves in a moment. They are Megan and Evan. But one more thing I want to say before they come on in is what the format of this show is. You see, the idea is that you can ask any questions you want. As you ask the questions appear here at the bottom, and then we note all of them. And if you're wondering how you type into the chat, you go to live.poshenlow.com/show, and then you can put any question that you want into here. And it says the instructions in the YouTube description if you're watching this through YouTube. Well, now what we'll do is we'll try to choose questions that are interesting to people who might be studying algebra or geometry. And oftentimes these are around the level of math competition questions. Okay, and we'll be here for about an hour. And let me now then turn it over to our two incredible hosts who will take it over from here. And they'll introduce each other. Go for it, Megan and Evan.
Yes, so as Professor Lowe mentioned, I am here today with the illustrious Evan. So Evan is great at mathematics. He's qualified for Amy multiple times. He went to Math Counts Nationals to represent Nevada. And he also is co-president of our school's math club with me, which is relevant to me because he's a great person to work with. And he also plays the violin. He doesn't just do mathematics, in case you were concerned about that. Yeah. Not violin, viola. He plays the slightly worse version of the violin.
Thank goodness. No, okay. Well, sure. Megan plays the slightly worse version of the violin, but of the viola. But apart from that, she also does math, specifically math competitions. She's gone to Math Counts Nationals for Nevada and has qualified for Math Prize for Girls. And as you may have already guessed, she's also a co-president of our math club. And she's also active in the local math club, volunteering over 100 hours per year, quite some time. And she speaks Spanish.
I see.
Yeah. Let's get started. What's our first question?
That is a very good question. I don't know if they've sent any yet. You guys should send in any questions you have to the same chat, and they'll get collected, and we'll solve them.
Yeah. Oh, I see one. 3. How many sequences of consecutive natural numbers add up to 2020? Okay. Sequences. The consecutive numbers that add to 2020. Okay. Well, I think it's okay just to do casework, but not terrible casework. Okay, sequences of 2 numbers, that would be a plus 1 equals 2020. But the problem here is that a plus 1 is 2a plus 1, which is odd. So you can't have an odd number equal to 2020. Instead, we'll have a sequence of 3 numbers. And the way we're going to make our work a lot easier is a sequence of 3 numbers can be written as a minus 1 plus a plus +1. And if this equals 2020, then we just want 3a to be equal to 2020. But 2020 is not divisible by 3. And then this is a bit of a shortcut, because every sequence of consecutive odd numbers can be written as, so a sequence of consecutive of k consecutive integers where k is odd, this is always going to be a multiple of k. And then I think we can use that to find the number of sequences of consecutive numbers that add to 2020 where the number of numbers in the sequence is odd. And then 2020, oh, I should know this better. This is 10 times 202, so 2 times 5 times 2 times 101. And 101 is prime. Yeah, 101 is prime, good. So we can have a sequence of 5 numbers, 101 numbers. Oh, actually, can we have a sequence of 101 numbers? Well, if we had a sequence of 101 numbers, we know 2020 equals 20 times 101. So we'd have to have 20 be the middle number of our sequence. So we'd have like 20, then 50 numbers ahead of it and 50 numbers behind it. But we want consecutive natural numbers. I didn't write that here, but it was in the question. And natural numbers just means 1 and up, so positive numbers. So we cannot have a sum of 101 integers, very sadly. And now even. I have a hunch that we can't have a sum of even numbers, and that's based on the idea that a plus 1, that was odd. Actually, no, that hunch is completely wrong. We can have a sequence of 4 consecutive integers. That would be a plus 1 plus a plus a minus 1. Wait, can we? Okay, let me just write out 4 consecutive integers.
Well, honestly, I'd like your method more. Like, just write it out. 6. If you subtract 6 from 2020, is it divisible by 4?
Yeah. No, because 2020 is divisible by 4 and 6 is not. What's a faster way though? Do we have any faster ways?
Well,
because this seems kind of tedious.
I think that you would have to consider, well, okay, if you have an even number of things that you are adding up, then the average won't be an integer. It'll be something 0.5. So
Right.
you would have to then have an even number of pairs or something. You'd have to take that into account, is basically what I'm trying to say. But there might still be a way to do it.
Yeah. So we'd have something 0.5, and now we're saying k is even. Something 0.5 times k, and this needs to be 2020. And 2020 is 4 times 505. So actually, we'd need k to be a multiple of 8, right? Because we'd have half something times half an odd number times a multiple of 8. That's going to be a multiple of 4. Okay, that makes it much nicer. This may not be possible. Okay, let's just try for k equals 8. Then we have some odd number, I'll call it O. O over 2 times 8 equals 2020. And then over here we said 2020 is 4 times 105. So 4 times O is 4 times 105. And this gives us O.
Why are you using O? O seems like a good way to confuse it with 0.
Oh, that's true. Oh,
like, I look at that and I see 0 divided by 2.
Okay. Some odd number n. N is sufficiently odd.
N's a pretty odd number.
What Ramanujan says. Okay,
I mean,
so n over 2
Ramanujan
times
agrees.
8. Yeah, I can't go wrong there.
No.
Implies n equals, well, here I wrote n equals n. I think we can do better. We can say n equals 505. This works because we can we? Wait, yes, we can definitely form 8 consecutive integers around 505 over 2. So we can have a sum of 8 integers. From there, I think we can say that if we go back to our equation of k over here, I think this is very important. So we have an odd number over 2 times k is a multiple of 4. So if k was a multiple of 16, then 16 times an odd number over 2 would be a multiple of 8. that 2020 is not a multiple of 8. So k can be at the maximum power of 2 that divides k must be 8. So we can write in the top right, 8 divides k, but 16 does not divide k. And then, then we have 8, k is 8 times an odd number. And will every odd number work? I don't think so, because can't we do a plus? Yeah, okay, we can use the formula for arithmetic progressions, but I want to try this way, and then maybe that might be faster. I don't know. Megan, could you see if that way's faster?
I think it'd be faster if we wanted to guess and check some stuff, like if we had a computer that would do it for us.
Sure.
But I think this way's more fun.
Yeah, I kind of like this way better. I am generally bad at guess and check. But then we have k is an odd number times 8. So why don't we just rewrite k with some odd number, I don't know, b. b is a generic number. b times 8. b is odd. And then we have to have b divides 505.
Mm-hmm.
Because otherwise there'd be some prime dividing the left side that doesn't divide the right side. In fact, we can get rid of that. So then I'll just take a jump here and say that our odd number times 8, it can be 8 times 1, 8 times 5, or 8 times 101.
I don't think it's 8 times 101.
Let's see. If it is, we need 808 numbers that add up. Okay, yeah, definitely not. You're right. 808 numbers that add up to 2020. We'd have tons of numbers, like 400 numbers here, and then 2020 over 808, and then 400 numbers over here. But there's no way 2020 over 808 is bigger than 400. So 8 times 101 is out, because that would violate the natural numbers requirement. So then I think all our numbers are 1, 5, 8 times 1, and then 8 times 5. Yeah, I think if you were the Eggman the third, I'd like to meet Eggman the second and Eggman the first. But yeah, it'd be way harder if they didn't have to be consecutive, because yeah, partitions. And that's actually what Ramanujan did, and that was very difficult. But yes, so we have 1, 2, 3, 4 sequences of consecutive positive numbers that add to 2020. Positive integers.
I'm not sure whether the choice to leave 40 as 8 times 5 is intentional, because we have 1, 5, 8, and 1 times 5 times 8, or whether Evan just didn't feel like calculating 8 times 5.
Let's leave it at 8 times 5 makes it more clear what I'm doing.
Okay.
Sure.
Sounds good. Well, you know what else sounds good? This next problem that has come in, that is something about ice cream. Let me bring this up for you guys to see, because I'm sure you'd like to see what I am reading. Okay.
We all scream for ice cream.
Oh, do we now? Can you guys see that? Hopefully. Such a great scream, Evan. I'm in awe.
Yes.
I'm even more in awe of these 3 flavors, which are chocolate, strawberry, and vanilla, of ice cream that are sold at Brian's ice cream shop. Now, Brian's friend Zerg gets a coupon for 10 free scoops of ice cream. The coupon requires Zerg to choose an even number of scoops of each flavor of ice cream. How many ways can he choose his ice cream scoops? Okay. And the order does not matter. Well, first thing I see that's important is he has to get an even number of scoops of each flavor. So at that point, even though he gets 10 scoops, it's 5 units of 10 scoops each. And so once we know that we have our 5 units of ice cream, 3 flavors, and order does not matter. So I want to use stars and bars here. So for those of you who don't know, stars and bars is a way to count the number of ways to distribute identical objects over different groups. We can call this not O, but let's just call it N. We can keep the groups as G. And this is going to be, since they're identical, order doesn't matter. So what we're going to do is we're going to assign our units to the 3 flavors. Now, just as an example of what we're going to be doing here, let's suppose, using the example of the problem, that he gets 6 scoops of vanilla, so that's 3 units, and 4 scoops or 2 units of chocolate. So we have chocolate, no strawberry, vanilla. Now, any arrangement of these 7 items would give us a different order that he does. So if for chance he had something like this, this would represent 1 unit of chocolate, 3 of strawberry, and 1 of vanilla. And we can just basically order these however we want. Now, this isn't too hard to do because we have a row of 7 objects, and we're going to choose 2 of them to be bars. 7 choose 2 is 7 times 6 over 2, which is 21. And in case you're wondering why I labeled N and G, that's because we can also call this N plus G minus 1 over N. Or not over, choose N. So that right there is our formula, and that right there is our answer. And that right there is an Evan who is trying to be speaking, but he has too much ice cream in his mouth.
Yes, exactly. Well, anyway, ice cream, it's wonderful, and there's someone hanging off. But I'm slightly partial, actually, to the stating of stars and bars as chopsticks and wontons. I really like that version. But same thing. And thanks, Megan, for also explaining how the formula comes about. That was good. And our next question is about John, who likes biking. Okay, it's a bit hot for that, but he's taking a 30-mile bike ride over hilly terrain where the road is always either uphill or down. Oh, okay. He's taking a 30-mile bike ride in San Francisco, and if he bikes at a total of 20 miles uphill, 6 miles downhill, 20 miles uphill and 6 miles per hour when he goes uphill, and 24 miles per hour when he goes downhill, what's his average speed? Okay, well, average speed, we can use the equation distance equals rate times time. And our average rate will be the total distance divided by the total time. And the total distance is 30 miles, but 20 of those miles are uphill. And how many are downhill? Well, it's a 30-mile bike ride, so 10 miles are downhill. Okay, when he's going uphill, he has 20 miles to go, but he bikes at 6 miles per hour. So it takes him 20 over 6 hours. Yeah, exactly. Eggman the 6th. Wow, there's so many Eggmans. Okay, we have 20 over 6 is how long it takes him to go uphill. And then, can you even bike at 24 miles per hour? That's very fast. But anyway, we have 10 miles downhill and 24 miles per hour when he's biking downhill. So that's our time, and that's our distance. And if we just expand simplify the fractions, we'll get our average speed. And this is just 30 over 10 thirds plus 5 twelfths. Actually, I could have saved some time by writing this as 30 over 40 over 12 plus 5 over 12. And I'll ask Mr. Tai to turn off so we can see this better. And this is just 45 over 12. This is 30 over 45 12s, which is 30 times 12 over 45. 15 goes into 30 twice, into 45 thrice. 12 over 3 is 4, and our answer is 8. Oh, that's a very good number, but 8 is his average speed. Yeah.
That makes
many fractions.
That makes sense too, I think.
Yeah.
It's definitely between 6 and 24, which you like to see.
Yes. Cool.
Very cool. Okay. Well, do you know what's even cooler?
Geico?
No, this other ice cream
Oh.
question that was submitted by someone in chat.
Oh.
Because ice cream, it's pretty cold, you know? That
Yeah,
makes it
yeah.
super cool. Yeah. Okay, this ice cream isn't that cool. It's grass, dirt, earwax, hair, and dust bunny flavored, with cones made out of granite, marble, or pumice, and topped in hot lava, chalk, or ink. Okay, won't the hot lava cool down though? Like objectively, I don't think that'll be that hot. Okay, how many ice cream cones can the evil confectioners in this ice cream land make? You get 1 scoop of ice cream, 1 cone, and 1 topping. Well, this seems like a great time to do the multiplication principle, which basically just says, if they don't affect each other, you multiply them all together. We have 1, 2, 3, 4, 5 flavors of ice cream, 3 cones, and 3 flavors of topping. So that's 45. And just to explain on a slightly smaller scale why we're doing what we did, if we think about it, let's bring it down to supposing it was 3, 2, and 2. I can draw 12 things. So our first choices is grass, dirt, and earwax. And then after that, let's do marble or pumice, and this goes for each of them. So we're making a little tree here. Marble, pumice for each of them. And then after that, it was what? Ink and lava. So as you can see, I've got a lot of stuff to draw out here. I'm not going to actually draw it out here because I don't feel like writing that much. But basically, for each of the 3 decisions we made here, we're going to have the same 2 decisions here and the same 2 decisions here. So we end up getting 3 times 2 times 2. And that is a lot of great questions coming in. Thank you guys a lot. That is an adorable bunny, Evan.
Yeah, it is a dust bunny. Okay, let's see. What's a good next question? In a quadrilateral pair. Okay. Oh no, I actually like this one a lot better. How many integers n? I'll paste that in right now.
Oh, yeah, I see the one you're talking about. That one looks cool.
Yeah. It looks fun. Actually, I'm hesitant to wonder why someone named a quadrilateral a pair, since that sounds something much more like you'd name an ellipse, but okay. How many integers n are there between 1 and 2017 inclusive, such that such that 1 to the n plus 2 to the n plus 3 to the n plus 4 to the n plus 5 to the n plus 6 to the n is divisible by 5? Okay, I'll write this more nicely. 1 to the n plus 2 to the n plus 3 to the n. Ooh, I see something about tau to the n. Very nice. Plus 4 to the n plus 5 to the n, or tau of n, plus 6 to the n. Okay, well, we're taking this mod 5. 5 to the n is always divisible mod 5, divisible by 5 for positive n. Out that goes. 6 to the n, well, that's equivalent to 1 to the n, which is equivalent to 1. And the reason for that is because 6 equals 5 plus 1. So when you raise 6 to any power, you're just going to have tons of things that are divisible by 5, and then a 1. So 6 to the n is equivalent to 1 to the n. Okay, 1 to the n, 1 to the n, that's just 2. So you have 2 plus 2 to the n plus, plus 3 to the n plus 4 to the n. And I see a shortcut. 2 to the n and 3 to the n. 2, or more accurately, 3 is negative 2. So this is 2 plus 2 to the n plus negative 2 to the n plus 4 is negative 1. So negative 1 to the n. And we want this to be equivalent to 0, mod 5. Right. I'm going to clear out the stuff above. We don't need it. And we're left with this. 2 plus 2 to the n plus negative 2 to the n plus negative 1 to the n is 0 mod 5. Well, if n is odd, this becomes 2 plus 2 to the n. And negative 2 to the n is going to be negative 2 to the n. Parentheses and negatives, they go along very well. And then negative 1 to the n will just be negative 1. The 2 to the n minus 2 to the n, they're going to cancel. And 2 minus 1 is 1, which is great. This is equivalent to 1 mod 5. 1 is not 0. So when n is odd, this is not true. Okay. Well, surely if n is not odd, it's even. So if n is even, what happens? This is 2 plus 2 to the n plus 2 to the n plus 1. Okay, and this is a little bit more work. N is even. 2 plus 2 to the n. The negative will go away if n is even. So this is plus 2 to the n. Again, the negative 1 goes away, becomes 1. This is equivalent. I'm not going to write equivalent to 0. We all know that's what we want. So this instead is equivalent to 3 plus 2 to the n plus 1. Whew. I mean, we could just start finding 2 to the 1, 2 to the 2, 2 to the 3 mod 5, but I see a slightly faster way. So since n is even, we can write n equals 2 times k for some k. n equals 2k for some k. And then this is equivalent to 3 plus 2 to the 2k plus 1. Or even better, this is 3 plus 2 to the 1 times 2 to the 2k. 2 to the 1, 2 to the 2k. And by exponent rules, we can see it coming out now. 3 plus 2 times 4 to the k. This is a really nice problem, or I find it fun. 3 plus, now this becomes 3 plus 2 times negative 1 to the k, because 4 is negative 1 mod 5. Actually, I should be writing mod 5 in front of all of these if I really want to be precise. Okay. 3 plus 2 times negative 1 to the k mod 5. Negative 1 is either 1 or negative 1. If negative 1 to the k is either 1 or negative 1. If k is even, this is 3 plus 2 or 0 mod 5, and we're happy. If k is odd, this is 3 minus 2 or 1, which is not 0, and we're very sad. So we want k to be even. K even. This is true only if k is even, if and only if k is even. But what do we say? N is 2 times k. Perfect. So n is 2 times an even number. So n is 2 times an even number. So n is divisible by 4. Let's see. What did we say? How many integers n between 1 and 2017 inclusive are there such that blah is divisible by 5? So how many multiples of 4 are there between 1 and 2017? That's just the 2017 over 4, or the floor of 2017 divided by 4. 4 goes into 20 5 times. 4 goes into 17 4 times. And this is the 0.25 we don't care about, because the next number, which is 2017, that will not work. It is not divisible by 4. So we have 54 numbers n between 1 and 2017 that make this expression here divisible by 5. And I think that's it. I do like this question.
I like that question too. But, I mean, I will say I've used the time you were doing that to draw a pair.
Ooh,
Okay.
That's a really good pair.
I've drawn 2 pairs, actually. So.
A pair of pairs.
Yeah, exactly. I'm so glad you noticed. So, for those of you who cannot read my mind and know why I drew this, here is the problem that we are solving next. And it's geometry, so I was getting a head start on our diagram. So, this says in quadrilateral pair, PE is 21, EA is 20, AR is 15, RE is 25, and AP is 29. I'm glad you guys like my pair. I tried to make them as similar as possible to just show off the true pairiness of them all. But anyhow, for the math, thank you, Cookie Monster. For the math part of this, I see 20, 25, and 15. And that is 5 times the Pythagorean triple. 3, 4, 5. So we know that this is a right triangle. 3, 4, 5 triangles show up a lot. It is very good to know them. Now, once I realize that, my next question is, how else can I use right angles here? And as it turns out, if you check this, I don't know this off the top of my head, but if you check the mathematics on it, 20, 21, and 29 is also a Pythagorean triple. So we've got 2 right triangles here. Yeah, just like Cam says, they're both right. They're both Pythagorean triples. So we've got 2 right angles, which makes this a trapezoid. And trapezoids are very easy to find the area of. Height, which we know is 20, times the average of the 2 bases. 21 plus 15 over 2. Well, I'm just going to go 10 times 36, which is 360. So in addition to being the number of degrees in a full turn, angle, whatever you call it, it's also the answer to our question.
Nice. That was neat. Very quick for a geometry problem.
It helped that I had the diagram, I will say.
Yeah. Although I wonder what would have happened if you tried using the pair, just assigning points here and there and seeing if you could get by just with the numbers and the lines.
Oh.
Maybe that's not such a good idea. Anyway, our next problem, kindly submitted by a viewer, asks us to find the sum of the, how many? 6 smallest n, such that, positive n, sum of 6 smallest n. Okay, sum of 6 smallest n, such that this is true. Okay, thank you, Eggman the 6th. Do you know if Eggman the 7th has a problem as well? I would have thought this is more of a problem by Eggman the 7th, because it has a 7. But then again, it also
has
wants
a
the
6.
sum of this. Yeah.
Yeah.
Okay. Eggman the 6.5. Oh wait. No.
Well, Evan, I must
Right.
ask, what is that odd T you've drawn there? What does that mean?
Yes, it's a tau. Tau of n counts the number of divisors of n. So we're gonna just take a little sidetrack and do a little bit with tau of n first, so we all know what it is. Taking, I don't know, 6 as an example, just to get started. Tau of 6. Well, how many divisors of 6 are there? 1, 2, 3, and 6. I'll divide 6. Quite a few. So tau of 6 is 4. Okay. And actually, you can do much nicer things by finding tau of a general prime factorization, like p1 to the e1, p2, e2, all the way to pk to the ek. And this is a product of primes to powers. And what we can say is that any divisor of this product of primes has to be a product of some number of the p1 through pk. Well, okay, a general divisor written in green, because green and general start with the same letter, I'm sure. It's
They
P1,
do.
yes, to the something, P2 to the something, all the way to PK to the something. What can we put in the first something? 0 through E1, right? So we have E1 plus 1 options for the power of P1 in a general divisor. And then for P2, well, the exponent of P2 in a general divisor, it has to be less than or equal to E2, because we can't have something like, oh, maybe 27 is a divisor of 36. That doesn't work, because 27 is 3 cubed, and 36 is 2 squared times 3 squared. Can't fit a 3 cubed into a 3 squared. It is a recipe for much weeping and gnashing of teeth. Instead, we can fit 0 through E2. So this is E2 plus 1. And by now, you probably see the pattern, and we can continue the product all the way to EK plus 1. So yeah, that's just a little tidbit about tau, the number of divisors function. We can leave that up there just for fun. But now we want the number of n such that tau of n plus 1 is 7. Well, what is 7? It is a very nice number, but it's also 1 plus 6, 2 plus 5, and 3 plus 4. And
what about 0 plus 7?
Oh, well, yeah, 7's also 0 plus 7. The thing is, no positive integer is going to have 0. Actually, no integer is going to have 0 divisors, because it'll always divide itself. So
what integers have one divisor?
Just one. 1. Ah, yes, the true 7 was the friends we made. That doesn't make much sense, but I like it. I like it a lot. So the only way we could have a 1 is if n was 1. And then our sum becomes tau of 1 plus tau of 2. Well, 2 is prime. Its only divisors are 1 and 2. This sum is 1 plus 2, or 3. And 3, as much as it tries to be, is not 7. So our possibilities are 2 plus 5, 3 plus 4, or 4 plus 3, and 5 plus 2. If this is tau of n, and this is tau of n plus 1. So in this case, tau of n equals 2, tau of n plus 1 equals 5. Huh, okay. Remembering that we want the 6th smallest n, I'm wondering about n plus 1. If tau of n plus 1 is 5, it has to be a prime to the 4th power. So here, n plus 1 equals some prime to the 4th. But 2 to the 4th is already pretty large. And 3 to the 4th I'm fairly confident that's not going to be among the 6 smallest n. Even so, p to the 4th minus 1, this is n. It has to be prime. If n plus 1 is p to the 4th, p to the 4th minus 1, or n, has to be prime because tau of n is 2. But p to the 4th minus 1 factors using difference of squares, which is very nice of it, into p squared plus 1 and p squared minus 1. And primes are greater than 2, greater than or equal to 2, and even 2 squared minus 1 is bigger than 1. So this is never going to be 1 times something. So n will always be the product of 2 things that are not 1, meaning n cannot be prime. And so there are no solutions in this case. Very sad. Okay, well, maybe we'll have better luck when tau of n is 3 and tau of n plus 1 is...
Oh, I was gonna say, what if we switch the order, but you are considering that in a later case, aren't you?
Yeah.
Smart.
I almost didn't. Oh, Adrian the 6th. Yes, it is spelled Terence, as in Terence Tao, but unfortunately, the last name is T-A-O, like you said. It would have been amazing to have a last name like that and be a mathematician.
I mean, you are a mathematician.
Some things are not meant to be. I am no trustworthy. Okay, I'll make sure not to trust you then, person the 5th. Okay. Now, what were we doing? Oh yeah, we're finding the number of n such that tau of n equals 3 and tau of n plus 1. I'm getting a bit tired of the screen. Maybe orange. Orange is nice. Tau of n plus 1 equals 4. Whew. Tau of n is 3. 3 is only 3 times 1, right? So what that's saying is that if tau of n is 3, n has to be a prime squared. So n, this means n has to be, or this is true if and only if n is some prime squared, because 2 plus 1 is 3. And if we had a product of 2 primes, well, then, no, if we had the product of 2 primes, like say some q to something, then the number of divisors of n would not be 3. It would be the product of 2 numbers greater than 1. This is not a wonderful explanation. Basically, 3 is prime, so we have to have n as a prime squared. But then tau of n plus 1 is 4. So this is true if and only if n plus 1 equals q and r, q times r, for some primes q and r. I think I'm running low on variables, but we could also have n plus 1 equals s cubed, right? Because 3 plus 1 is 4, but 4 is also 2 plus 2, hence qr. Okay, I am going to move this to a new page to see if there are any solutions for that.
I might have a couple.
Use, someone says use O again. Okay,
as
sure, I'll use that for my next variable. Yeah. Whew. Yeah, I sure hope we have some solutions. That would make my day.
Well, I think we do.
Let's just try some prime squared. Wonderful. 2 squared, 3 squared, 5 squared, 7 squared, and 11 squared. Just to be safe, we'll go up that high. So then n is 4, 9, 25, 49, and 121. So this is n. Then n. In that case, n plus 1 is 5. Oops. 5, 9 plus 1, which is 10, 25 plus 1, which is 26, 49 plus 1, which is 50, or 122. And now we want to see which of these are a product of 2 primes or a prime cubed. 5 is prime, doesn't work. 10? Hooray! It's 2 times 5. Woohoo! Okay. 26? Oh, yay, it works as well. Okay. 2 times 13.
Evan's
50.
so excited. I love it.
Yeah, I'm really happy because I was worried we might have to go above 100, and I don't want to do that for all the cases.
We might have to go above 100.
Oh. That's a very suspicious person. 122. 2
You
times
can't accuse
61.
everyone of having committed murder, Evan.
Now I'm... Keep that on the down low. No.
Did you commit a murder, Evan?
No, of course not. Don't worry about it.
Good. Well, I wasn't before.
Wow, that's a lot of stars, math lover. Why doesn't 26 get smile? Okay, you're right. I've been awfully unfair to 26. I'll give it smiley faces and check marks as well. And 122, that's twice 61. So it gets smiley faces and check marks as well. Woohoo! Okay. We're good with this case. We found 3 solutions, and I hope that we'll be able to find more solutions smaller than this so that we don't have to go back further, but we may need to.
Evan, I'm very excited as well. If you look at...
Whoa. Wow, those are neat lights. I
They
think they're happy
are.
for 122.
They are. 122 is a great number.
Yeah. Right. What do we have now? Okay, in long problems like this, it's kind of easy to lose track about what's going on, but we found that tau of n plus tau of n plus 1 equals 7 means that tau of n is either 3, 4, or 5. Then we found some solutions for when tau of n is 3 and when tau of n plus 1 is 4. So now let's find some solutions for when tau of n is 4 and when tau of n plus 1 is 3. Okay. In this case, just like before, tau of n plus 1 is 3 means n plus 1 is some prime squared. And we can go through some prime squared and check that tau of n equals 4, which means n is pq or r cubed. Whew. As before, the primes squared were 4, 9, 5 is the next prime, 25. The next prime after 5 is 7, which is 49. After 7 comes 11, which is 129. No. 11 squared is 121. And then,
Wait,
as
Evan,
Professor Lowe likes to say,
you're not going to have a lot of luck here since you're basically taking a square and subtracting it by 1 squared. So you'd have to get really lucky to have that be a prime times a prime or a prime cubed.
Wait, that's true. That's true.
I know,
Megan is
that's
very
why I said
smart.
it.
She saved us some time. Yes, n equals p squared minus 1 equals p plus 1 times p minus 1. But I don't think it happens very often that you have 2 consecutive integers be prime, because one of them needs to be odd and one of them needs to be even. And there's a notable lack of even primes.
I mean, we should check
okay.
too. We should check too.
Sure. But in the case of 2, 2 squared minus 1 is 3, which is prime. Tau of a prime is 2. And this case is done.
Wait, what about if it's a prime cubed, though?
A prime cubed?
Because that was another case that we had, right? Prime times prime or prime cubed.
Oh, that's true. You're right. So we only need to check for that. And I think that is sometimes true. Yeah. Oh, yeah. Is it true beyond 3 squared minus 1? I'm not sure how I prove that it isn't.
Parity? Because a prime squared, when the prime is greater than 2, is always odd. So if you take an odd number and subtract 1, it's always even, and the only even cube of a prime is 2 cubed.
That's very smart. I like that idea. But we don't have to prove everything thoroughly here. If you follow Megan, that means that the only solutions in this case are n equals 8. Okay. We should add them to our solution wall. Let's make a wall of solutions up here. Or like a hedged out
Beautiful.
garden where they can't escape. With yellow wallpaper.
Isn't that called a prison normally?
Yeah. Or literary
Cool.
analysis. 10, 26, and 122. No, I mean yellow wallpaper, the short story. No, that literary analysis is prison. It's not. 10, 26, and 122. Oh, this
I'm
is taking a
clipping
while.
that and sending that to our English teachers, you know.
No! Yeah, that would be taking it extremely out of context.
I know, that's the point.
Oh, I'm very disappointed in you.
When are you not?
Okay, fair enough. Sure. If you want, we can jump to another question, but I think we're very close to finishing. I can whisk through
Yes.
this part. If tau of n is 5, then n is a prime raised to the 4th power. Tau of n plus 1 is 2. N plus 1 is prime. Okay. This is possibly true. Yeah. When p is 2, p to the 4 is 16. When p is 3, p to the 4 is 81. And then 16 plus 1 is 17. That's prime. Perfect. So n equals 2. Wait a second, what? Oh no, so n equals 16 works. And we'll put that on our happy solution wall. What else? Do any others? Well, okay, 1, 2, 3, 4, 5. We have 5 solutions. So the next one is 5 to the 4. That's going to be too big. Okay, so yeah, we unfortunately do have to return to this one and find some more primes. 13 squared is 169, and this is 170. That doesn't work. This is taking a while. Should we just move on? Do you think?
I mean, maybe. I will say, we can either problems that I see that our moderators have put up. There's either 2 simple ones we can do or 1 more complicated one. We probably have just about the time to do either.
Yeah, actually, let's do the simple ones or the less complicated ones, because those ones are definitely more what this is geared towards, like middle school math competitions. But yeah, you can continue, finish the cases, find 2, 3, 4, 5, find 1 more small solution, and you're done. And
yes,
this is still a nice problem.
Very. Okay, well, the other one that we have that's a bit quicker is a bit more on the demented end. So I've gone with this one, very numbery, very non-demented. Compute the sum of the prime divisors of 2 to 40. You can see the numbers, those numbers. 2, 4, 5, 4, 5, 2, 5, 2, 4, and you sum them. Now, you might notice this has a 4, a 5, and a 2. This has a 4, a 5, and a 2, and this has a 4, a 5, and a 2. So, in effect, this is 5 plus 4 plus 2 times, 100 plus 10 plus 1, because it appears in both of those places. So now we just have to figure out which of these are. 5 plus 4 plus 2, that's 11. 110 and 1 is 111. And while 11 is prime, this is actually 3 times 37. Then we just have to sum them. 3 plus 37 is 40. 40 plus 11 is 51. And we can check this if we want. Like, we could actually do the addition, check that it's 11 times 111, but I'm pretty confident in that, so I think instead I'll just leave the rest of this time to the other slightly demented problem we have.
Is this the one? Oh, I see what you mean by demented. Is it about turkeys and elephants?
See, okay, pull this question up, and I want to point out something about this question.
Okay, we have mutant... What?
So they have mutant green turkeys and pink elephants. Elephants don't have to be mutant to have 4 legs and 1 head. A normal elephant has 4 legs and 1 head.
That's true.
I don't know if you're aware of this.
Yeah, but you could argue that elephants are kind of demented in and of themselves. They're very odd.
But they're smart. And they're good listeners because they have those big ears.
Oh, yeah. Okay. Yeah, this one just seems like systems of linear equations. Unless there's a faster way. We'll probably find a fast way to solve them. Okay. Mutant green turkeys. Let there be G turkeys. And P pink elephants. Then there are 100 legs. Green turkeys have how many legs? 6 legs. So 6G. I don't want to meet this turkey. I really don't. But pink elephants have 1 head.
I mean, turkey legs is like a common type of food, isn't it? So maybe it's just
really?
like created for the food industry. Yeah, it's like at like festivals, right?
Oh, yeah, yeah. I was thinking about ostriches, the ones that kick you and all that. Thankfully.
I don't think we eat ostriches. They're too violent.
Yeah, and maybe endangered or something.
Okay. Someone's requested a drawing. I'll do that while Evan does the mathematics.
Yes.
I'm not good at drawing. I'm just warning you now.
I look forward to Megan's drawing. She is good at drawing mutant things. 3 heads for green turkey, and 1 head per elephant. Aha, I see. Yeah, Cam, I don't exactly have a pink pen on hand, but yes, Ramanujan is right.
I have a pink
there
pen.
Should be. Oh, for the elephants, yes.
Yeah, it's beautiful.
But we should have a 4P here because each pink elephant has 4 legs. And then this counts the number of heads. How many heads are there? 37. Yeah, I think we can just take the second equation and write 12G plus 4P equals 148, if I did that correctly. Yeah, 120 plus 28, and that's 148. And then subtracting this equation from this equation gives 6 times G equals 48. So G is 8. And I think that is 8 too many in existence. But then from G is 8, P plus 3 times G is 37. So P equals 37 minus 24, which is 13. So
awesome.
P equals 13. And we have 21 animals grazing. And 8 too many turkeys.
Okay,
Oh,
well,
wow.
as requested,
That's a good diagram.
Here's my diagram. They're beautiful. Not enough turkeys. Evan, is that what's producing these turkeys?
Yes. The nice turkeys pop. I have the drawing on call. Maybe they're put through, what are they called?
Well,
especially Eclair electric chairs. I don't know.
Oh my goodness. That is the last problem of the day, and thankfully also the last demented turkey of the day. Thank you guys for coming. What else do we have? We have another Ask Math Anything that is soon.
Very soon.
It's tomorrow night at 7 p.m. Eastern. And tonight there is also a Math Kangaroo live solve, I believe. If any of you guys do Math Kangaroo and want to see more of me, I will be there.
Yes, you should attend. Megan is good.
There is no Kangaroo live solve tonight. What is tonight? Shoot. There is something tonight.
Huh? There is a demo course, but
there's a demo course tonight. If you guys want to take
5 p.m. Eastern.
If you guys want to take courses with us, the demo for that is tonight. If you do Math Kangaroo and would like to see us live solve the problems from that, those are every Friday night. But there was one yesterday, so that'll be in 2 weeks. Sorry, we have a lot of really cool stuff. If you just choose a random night, we're probably doing something. But thank you guys for coming. Goodbye.
Thank you very much for coming. Goodbye.